Hello and welcome. You are looking at parallel and perpendicular lines, a whole overview of them with example problems, and it'll be covering this entire span of stuff. So you can go and take a look at those. I'm just going to jump straight ahead to save time. Okay, there's going to be stuff that's on the top frame right here, and I'm not going to be reading off of them, but I'll be saying things off of here as well. So you can feel free to read what's up there, and it pertains to the example problems that you're looking at. So for numbers 1 and 2, we're going to use a protractor and a centimeter ruler. We're going to classify each triangle by its angles and its sides. So based on whether certain things are congruent or obtuse or 90 degrees or pairs of congruent, like all that kind of stuff we're going to look at. So for number 1, I want to measure each of these angles and each of the sides. This first angle measures to about 66 degrees. Put that right there. This second angle right here also measures to about 66 degrees. Let's go and place that one right over there. And the final angle should measure to about whatever 66 plus 66 becomes some value, 132. When you subtract that from 180, you should get about where you're at. So that one's 49. So that's close enough. Obviously, the protractor had some little issues, but 66 plus 49 equals 181. So it should be 180. But the bottom line is these two were congruent. The third one was not. So I have two congruent angles. So already I'm matching the definition of an isosceles triangle. Now to confirm that, my legs, or my sides, here and here should also be congruent. Let's check that out. Let me first delete this one and go to the ruler. So this first leg right here looks to be about 2.3 centimeters long. And the second leg right here also looks to be about 2.3 centimeters long. And the third one will be the shortest one. Let's go ahead and ignore that one for now. We know that these two are congruent, so we're looking at an isosceles triangle. And more specifically, all the angles are less than 90 degrees, so it is an isosceles acute triangle. And that's what that one is. Okay, the second one, let me pull out the protractor again so we can take a look at this. Let's measure up some of these angles here. This first angle here, let's get it over, looks to be about 131 degrees. So let's go and put that right in there. This second angle right here appears to measure out to about 22 degrees. So let's place that there. Now I'm going to eliminate the protractor. Let's talk about how to get that third angle again one more time. So if this is 22, and this is 131, and this is x. So 131 plus 22 plus x equals 180 degrees. All right, 131 plus 22 is 153. 153 plus x is 180. So x will be about 27. Those angles are pretty close to each other, but I think it was measured well enough to say that these are not the same angle measures. And if they were, keep in mind, then this segment would be congruent to this segment. And just through an eye test, it doesn't look to be that. Let's check that with the ruler. So this first one here looks to be about almost 2.3 centimeters again, just like that other one was. And this side right here looks like it's less than 2 centimeters. It's about 1.8, 1.9 centimeters. So they are different, and by a substantial enough amount to know that these are not congruent. So this triangle is not isosceles. In fact, none of the angles appear to be congruent, neither do any of the sides. This side appears to be the longest one. This is called a scalene triangle. And also there is one angle that's greater than 90 degrees, so it's also obtuse. So it's a scalene obtuse triangle. Okay, numbers 3 and 4, we are going to find the measures of angle 1 and 2 and justify each answer. So right here, what you're given are two lines. These arrows indicate that they're parallel, and then there's a transversal that cuts through there that creates the angle 65 and 2 and 1. Angles 65 and 2 have a very distinct relationship. They are alternate interior angles with each other, 65 and 82, AIA. And when alternate interior angles are present, when they are made by cutting two parallel lines by a transversal, those would be congruent. So angle 2, its measure, is 65 degrees. Measure of angle 1 is a vertical angle with angle 2, and vertical angles are congruent, so the measure of angle 1 is also 65 degrees. Another way we could have gotten the measure of angle 1 was saying 65 and 1 are both corresponding angles with each other, and when lines are parallel, corresponding angles are congruent. So that solves for that one right there. Number 4, I have angles 1 and 2. Angles 1 and 2 are corresponding with each other, but if these are the two lines, and this is the transversal for which they correspond, they're not congruent. So I don't want to make any statement like that. But I can, with 85 and 1, I can tie a relationship. These are once again alternate interior angles. If these are the parallel lines and this is the transversal. So the measure of angle 1 in this case is 85 degrees, much like that angle right there. Now angle 2, like I said, does not relate to this one. These lines are not parallel. So although they're corresponding angles, they're not congruent. But 70 and 2, they're same side interior angles where with this transversal and these two parallel lines. And same side interior angles are supplementary. So if I add 70 with 2, I should be getting 180 degrees. And if you subtract 70, you're going to get the measure of angle 2 as 110 degrees. So that's numbers 3 and 4. Let's do a few more. Numbers 5 and 6, same idea. Now we have two sets of parallel lines in this one. Angles 1 and 2 are same side interior angles with each other, with this set of parallel lines and this transversal. So I can figure out measure of angle 1 by looking at this 85 right here because I have this set of parallel lines. 1 and 85 are corresponding angles and they are congruent. So the measure of angle 1 is 85 degrees. Now I can't make a jump straight from 85 to 2. They have no transversal going through, the same transversal going through both of them. So I have to get to angle 1 to now get to angle 2. Now just like that last problem, 85 plus the measure of angle 2 should be giving you 180 degrees because 1 and 2 are same side interior angles and 1 is 85. So when I subtract 85, I'm going to get the measure of angle 2 is 95 degrees. So there are those two right there. All right, number 6, you can look at, I'm going to do angle 2 first, just so we talk about something different. 70 and angle 2 are a linear pair. They are adjacent angles that form a straight angle. So when you add them together, they are also supplementary. They should add up to 180 degrees. So 70 plus the measure of angle 2 is 180 degrees. So the measure of angle 2 is 110. Now the measure of angle 1 plus the measure of angle 2 is also 180 degrees, and you could solve for it that way. But 70 and 1 are corresponding congruent angles, so angle 1 is 70 degrees as well. Okay, here's some words and not really any drawing, but make sure that you still understand what we are looking at here. Two lines are parallel and cut by a transversal, so like that. Write yes or no to indicate whether the numbers given could be the result or could be the measures of a pair of same side interior angles. Okay, so like I've just been mentioning, with same side interior angles, like say this one and this one, they have to be supplementary. They have to add up to 180 degrees. So basically add up 7, 8, 9, and 10 and decide which ones add up to 180. 7 and 8 do. 9 and 10 do not. So 7 and 8 are yes. 9 and 10 are no. So you don't need the visual, but I wanted to make sure you knew which ones were same side interior angles and then know whether they should be congruent or supplementary. So while 60 and 60 are congruent, 27 and 27 are congruent, with parallel lines, same side interior angles must be supplementary. Now 90 and 90 are congruent, but they add up to 180 as well. All right angles are both congruent and supplementary, and 40 and 140 are just supplementary. Okay, numbers 11 and 12. We're going to find the value for x for which line L is parallel to line M. So the same idea, only now they tell you that it's parallel instead of drawing the arrows. And now we have to solve for the variable as well. So here you have a combination of alternate interior angles with parallel lines, 14x minus 5 degrees. Now alternate interior angles are congruent when lines are parallel, so 14x minus 5 equals 13x. So to solve for x, I'm going to subtract 13x on both sides here, and I'll get 1x. I'm going to add 5 on both sides here, and I get 5. The instructions only ask to find the value for x. They did not ask to find the angle measure. However, if you wanted to find it, you could substitute 5 in for 13x, or into the expression 13x, or into the expression 14x minus 5, and you should be getting the same number. So it's still a good double checking measure, even if you don't need to solve for it. Now these two right here, when these lines are parallel, we're looking once again at same side interior angles, and these are supplementary, not equal. But when I add up 5x minus 20 with 3x, those two angles, I'm getting 180 degrees. 5x plus 3x is 8x. When you add 20 to both sides, I'm going to see 8x equal to 200. Divide by 8, x equals 8 quarters, 200 cents, $2. X equals 25, which makes this angle 75. 3 times 25, and then this should be the supplement of that, 115. If I did that right. No, 105. See, I didn't do that right. 105. Okay, numbers 13 and 14, more of the same, but now there's a big difference when it comes to what you're looking at here. We have extra lines that are kind of bugging us a little more so than the last ones we saw. 2 lines cut through a transversal, 2 lines cut through a transversal. These have 2 lines that are parallel still. Now they're cut through multiple transversals. Now I have 2 of them, and a triangle's made, and it can be a little confusing. But what I do recognize here is that this is 126 degrees, this is a transversal, and here's an angle measure that's formed from the transversal and the other line. Now this angle and this angle, if you look hard enough, are are alternate interior angles, and they're congruent to each other. Now 10x is this portion here, 11x is this portion here. And the angle addition postulate says if you add your 2 angle measures together, you should get the larger angle. So I should set these equal to each other because alternate interior angles are congruent. So 10x plus 11x is 21x. When you divide both sides by 21, you should be getting x equals, what is that, 6? So that's what x is, and like I said, always substitute in to double check that gives you 126. This one, once again, has a lot more to it, but find lines L and M. They are parallel. Now look for your transversals and decide which ones are most necessary for you to pay attention to. Well, this angle right here is 2x minus 30 degrees, so it looks like if I'm referring to these parallel lines, this is the transversal I should be paying the most attention to. This transversal says very little to nothing about this 2x minus 30, but it does help define angles x and 45. Now if you look hard enough, you can see this is 2x minus 30, and 45 and x create this angle right here, the angle that's formed. And if you ignore this line completely and just look at these 2 parallel lines in this transversal, you're looking at alternate exterior angles, and alternate exterior angles are also congruent. So if I create an equation, it would be 2x minus 30 is equal to the sum of these 2 angles, x plus 45. And solve for x, subtract x over, and add 30 over. You're going to get x equals 75. And there you are. So again, it's really a matter of trying to remove lines that are unnecessary for you to make sense of what angle relationships are being formed and what math you want to use. Okay, here's some construction. Number 15, draw a line M and a point T not on the line. So I took care of that for you. Construct the line through T perpendicular to M. So the way that I'm going to go about this here is using my compass. I would love to be able to construct an arc that goes through this line down here. It swoops at 2 different points and it comes back out the other side. So something like that. Because what I want to create here are endpoints here and here, where the segment made between these 2 endpoints is going to have a midpoint when I draw T through it. or when I draw the line that's perpendicular to the line through T. So now that I've drawn that arc, I want to create this like any other perpendicular bisector. I'd love to just go ahead on this side over here, lessen the width, and create a cross section down below with two separate arcs like this one. That's etching very, very, very close to my midpoint though. And this one right here. So the X that was made will coincide with a line that if I draw it through T, it will also go through that point. Now that is how I make my perpendicular line right there. Now I didn't need to draw a full arc all the way up here because T is already a point that I'm going to use, so I don't need another point up there. I just needed a point down here where I drew my X, and I'm good to go. So that is perpendicular to it, and it is through T. And there you are. Number 16, draw an angle ABC. I happen to make mine very obtuse just for the heck of it. Then construct line M through A so that M is parallel to BC. So let's pretend that A is a little farther down. I drew A way out there just to make it down there. So that one's A right there, that point. I'll just put it right here. And to make it parallel to BC right here, what I'm going to have to do is create congruent corresponding angles, because the converse of the corresponding angles postulate says if corresponding angles are congruent, then lines are parallel, or the lines that are made. So to create congruent angles, I'm going to start with my original angle, and at the vertex, look for an arc to make there that passes through both sides. I'm going to repeat this here on my point A. Remember, this is where line M is going to be drawn through. I didn't need to make it that big, but that's all right. Now from here, I'm going to find my points of intersection from my original angle right there. Let's stretch this width out. So let's find out what that width is. I'm not going to be able to make it perfect. That's as close as I can make it. So as I do that here, let's just stretch that a little past it. If I make this arc right here, that point of intersection is where my line M should be going through. It should be going through both A and that point of intersection. So like I said, it wouldn't have been perfect because my tool can only do so much. But let's say that was about it. It goes through A, it goes to that point of intersection. That is line M. And line M is parallel to BC because these two angles here are congruent. This one and this one. And when corresponding angles are congruent, with the transversal cutting through those two lines, then those two lines are parallel. There you are. Okay, I got an open-ended question for you. The letter F illustrates a pair of same-side interior angles and a pair of corresponding angles. So here are some same-side interior angles, 1 and 2. In the letter F, they're most often 90 degrees, so they're congruent. And then it also has corresponding angles here and here. And those are definitely congruent. And I think they're also 90 degrees. Find a letter that illustrates alternate interior angles. Okay, so I have the alphabet here for you. We're going to find alternate interior angles. Now, in order to do this, it's not that I need parallel lines, but I do need two sets of lines where, well, first of all, they got to be lines, not curves. So I'm going to cancel out some of these, but I want two sets of lines that are going to be kind of easier to focus on. But let's take out B, C, and D here. We're not looking at anything there with sets of lines that'll work. We've already done F. G won't work in this case. H might be good. I doesn't have angles. J neither. I might look at K in a second. Let's see what that has to offer. L doesn't have two sets of lines cut by another line. Oh, I'll see what M features. N, O, P, no. Q, no. R's got them curves. It's going to be an issue in a way. I'm going to not deal with that. No S. T, no two sets of lines with the transversal. U, no. V, no two sets of lines. W could. I'll show you why it could. X doesn't have two sets of lines going through that. Neither does Y. And we'll keep Z. So we're going to look at A, E, H, K, M, N, W, and Z. Okay, A. Here's the thing with A. Lines do not have to be parallel for you to have alternate interior angles. So these two lines are cut by this transversal right here. Here are sets of alternate interior angles. Okay, now they're not congruent because the lines aren't parallel. Here are also sets of alternate interior angles, and they're also not congruent because the lines are not parallel. But they are alternate interior angles. So A works. That's good. Let's take a look at what E has to offer. One problem I foresee with E is no real transversal that allows for an opposite side. So although these lines are even parallel, these sides don't extend in such a way that we have alternate interior angles. So I think E is an issue that we cannot create such an instance, unless I'm not seeing something here. But I'm not seeing any other transversal. So E is a no-go. Let's get rid of that one. H is perfect for this kind of thing. Alternate interior angles, boom. And if those are right angles, then they're congruent. And alternate interior angles here, same idea. So H is good. Now let's take a look at K, because even I need to see this one for myself. I'm having some trouble perceiving what we got here. So if K is drawn like this, like in such a way that it's not connected down here, but rather it's connected up there, then I do have alternate interior angles. But again, this is just my font, so maybe that doesn't pan out the right way. But for instance, this right here and this right here, those are alternate interior angles with one another. Because if this line kept extending, whoops, if you can see that line keeps extending down like that, and this line over and this transversal, yeah, those are alternate interior. Do I have another transversal I can work with? I don't think so. So I think that would be it for K, but K does work only if the letter is drawn like that. M, let's see here. I have, okay, so here, so let's take a look. I'll draw it differently, but let's take a look at this green right there. And if I extended this as a transversal, it's not saying that I can extend it. I'm saying for your perception, if these are extended, take a look at this angle and this angle right there. Those are alternate interior angles in M. Those two. And obviously on this side, that would be the same thing, also alternate interior angles. But again, not congruent, just alternate interior. Okay, and I think you can see me go on and on with that. So let me just do a few more. Let's see, W would be the same case as M for that reason. Z and N are perfect ideas of alternate interior, alternate interior. So the only case that didn't pan out for me there was E. So A, H, K is an exception. Let me asterisk that. It depends on your font. M, N, W, and Z. And I hope I didn't miss anything else. Open-ended, describe two corresponding angles formed by lines in your classroom. I'll try my best. So it looks like there's pictures of my classroom here. So if you can see right here, it looks like I can have two lines cut by a transversal, and then those would be corresponding angles right there. These on the floor down here are tiles. So you could just say any part of these tiles can create corresponding angles like those two right there. But they have to go through some lines. You know, right here, once again, same thing with that tape, corresponding angles. So I won't be looking around too much, but those are some designs over there. Just look around for different lines. Over here, even the windows, maybe, if you think about the fact that these are going down with the panes right there, I have corresponding angles here. Okay. Take a look at these pennants up here. Okay, I have lines going like that, so these are corresponding angles. Now these ones that I'm doing are also congruent, right? All corresponding congruent angles. Even on the ceiling, if you kind of see these lines up here that are made, you'd have corresponding angles. So a bunch can be made all around, but I only want to do things that are connected in such a way with a transversal. And all these ones seem to be right there. Okay, here's a two-column proof. Most of the stuff is kind of given for you in the sense that they give you the statements. We have to figure out the reasons for them. L is parallel to M, that's given. And angle 4 is congruent to angle 2, that's also given. So we already can figure out 1 and 3 just by saying they're given. We have to prove that N is parallel to P. Now, it is missing a final statement here, so we're going to have to figure that last part out. So, we're given that L is parallel to M. If that's the case, then we can take a look at some sets of transversals here, such as if these are the two lines, then here's a transversal going through those two parallel lines. That would make angles 1 and 2 congruent to each other. Why? Because they're corresponding angles, and corresponding angles are congruent when lines are parallel. So I'm just going to put corresponding angles. That's the postulate, though. Angle 1 is congruent to angle 4 now also because angle 2 is congruent to angle 4. So if angle 2 is congruent to angle 4 and angle 1 is congruent to angle 2, then angle 1 can be congruent to angle 4. You could either say substitution or the transitivity property of congruence. So substitution property of congruence or transitivity. Either one would seem to fit here. Transitivity. Transitivity. There we are. Now, we still need a statement number 5. Okay, we have to make our final statement that line N is parallel to line P. Now, how can we make such a statement? Well, we have angle 1 congruent to angle 4. Once we prove those two were congruent, then those lines became parallel. That's the converse of the corresponding angles postulate. So converse of corresponding angles postulate. Let me write that. So one way the postulates work or theorems work is that when lines are parallel, those relationships are congruent or perhaps supplementary if you're talking about same side interior or same side exterior angles. The converse is also true though. If the angles are congruent and they're corresponding or alternate interior, alternate exterior, or they're supplementary and they're same side interior, same side exterior, then the lines are parallel. So once I had that transversal and I found out these two lines were congruent, then I knew those two lines were parallel. That's the final statement. Number 20, let's write an equation of the line with slope of -5 and containing the point 3, -1. That's point A. So I included a graph for you so we can take a look at that and make sense of what we're talking about here. Here's the point -3, 1. If you know anything about slope here, that -5 is -5/1, so which means every time I go down 5, I also run 1. Looks like I'm running out of room to do the rest there. So let me go up 5 and run to the left 1 a couple times. Okay. So what we're going to do is we're going to, after graphing this, we're going to write the equation of the line. We'll do it in two different forms, point-slope form and slope-intercept form. And let's see how well I can kind of get this doing its thing. Close enough. Not close enough. Let me try this one more time. All right. So there's my line. And you can tell it's passing through the y-intercept kind of high up, maybe around 15 or something like that. We'll take a look at that. First form I'm going to do is called point-slope form. Now, point-slope form is it's an equation where slope and a point are easily identified. So here's y minus y1 equals m times x minus x1. That's the formula, where m is your slope, such as -5, and x1 and y1 are your 2 points here that they are giving you. So that's y minus -1, because remember the minus is in front of the y1, and that's our y1 value, equals -5 times x minus 3. So there is, when I change this to y plus 1, equals -5 times x minus 3. That is a perfectly acceptable equation right there. It's in point-slope form. You did what you needed to do. You're good. You're set. And you could stop. But let me also tell you what point-slope form is about. If you know any other points, you could also use any of them. For instance, I know this point right here is one of the points because I graphed it. So this point is 2, 4. So I could have also written this equation as y minus 4 equals -5 times x minus 2. Now there would have been no reason for you to do that because you had to find that one, whereas they already gave you one. But this is going to help me show two things. Well, this is going to help me show one thing, and I'm going to use that other thing to help me show another thing with this graph. One is that you want to know that these are the same equation, even if they don't look it. Any points that are solutions to the line will be on that line itself. So any of these will work for point-slope form. And let's test that by putting these into slope-intercept form. And you do that by solving for y. So on this first one, I'm going to subtract 1 onto the left side. I'm going to distribute the -5 into x and -3. -5 times -3 is plus 15. And I'm going to subtract that 1. So that becomes -5x plus 14. So this is slope-intercept form for this first equation in point-slope form, from point-slope form. The second one going from point-slope form to slope-intercept form, let's add 4 to both sides, meanwhile distributing the -5 into the x and the -2. And like I said, I'm going to add that 4. So this becomes y equals -5x plus 14. And look, they're the same thing. And they should be the same thing because these were both solutions to this line. They are points that are on the line. And even though they look different here in slope-intercept form, which you might prefer, they end up being the same thing. Now, if you think about this being 14, that's your y-intercept. So it's crossing at, here's like point 10, 11, 12, 13, 14. So that makes sense that it goes about up there. It's not perfectly accurate, but that makes sense there. A third way you could do it is going straight into point slope-intercept form without point-slope form. So what I would do, and this is probably what I do most of the time, y equals mx plus b, I know the slope, and I need to find the y-intercept. So what I'm going to do is use this solution that I know, 3, -1, substitute it into my equation here to solve for b. So I'm going to get -1 equals -15 plus b, and when you add 15 to both sides, you're going to get b equals 14. So your equation one more time becomes y equals -5x plus 14. It's just about how you attack it. A lot of different ways. We wrote the equation. You didn't need to graph it, but that's not to say the graph doesn't help. Now, there's also standard form that this could change into, and this would come pretty simply with this equation here. I just have to add 5x to both sides because standard form looks like ax plus by equals c. So if I add x to this side, I'm going to get 5x plus y equals 14. Sometimes standard form doesn't come easy because you have fractions and because your x becomes negative on this side. You want your a value to be positive. I didn't write that, but that's going to help that as well. Okay, number 21, explain how you can determine whether a polygon is concave or convex. Let's make sure we separate the two by drawings. Concave polygons are more irregular type. Maybe it looks something like this. Okay, convex polygon, let me just pull out my polygon tool, just make a pentagon for you. So here's a convex polygon, here's a concave polygon. Now a concave polygon has a couple of things going for it. A concave polygon will have at least one convex interior angle, so something that's greater than 180 degrees. Meanwhile, a convex polygon will have concave interior angles, meaning all these are less than 180 degrees. So that's one way of doing it. The only problem with that is you use the opposite word for it to help describe it. So that's probably not going to be your favorite definition. My favorite definition, and it's probably most textbook definitions that they'd mention, is regarding the diagonals. The diagonals in a convex polygon are all going to be inside of your polygon itself. So all these diagonals that go from one non-adjacent vertex to another will make that happen. And I made a star in the pentagon. Beautiful. This one here, however, although I can make a bunch on the inside of my polygon, there is going to be at least one here that's not going to fit the bill, and it's this guy out here. This diagonal lays outside of the polygon. So explain how I can determine whether the polygon's concave or convex. Are there any diagonals outside of your polygon? That's the question that you'd be answering. Looks like I'm missing this one right here. And there we go. So that one's pretty important to know. Now it's also important to know that although this is a concave polygon, and it's actually a hexagon, it has 6 sides, the angle sum, which we're going to get into I think in a moment, the angle sum is still the same as another hexagon. So let's say I drew a regular hexagon, probably should have done that one first. But this hexagon has an interior angle sum that is the same as this one. I think they're both 720 degrees. Okay, so make sure you're understanding that. Even though it's concave, it doesn't change that the sum is still 720 for a hexagon, or whatever it is. Okay, 22 and 23. So now I have a 1, 2, 3, 4, 5-sided shape. That's a pentagon here. It also has 5 angles. Now the interior angle sum is done by this formula here. The degree sum is 180 times n minus 2, where n is the number of sides. Now that's also equivalent to how many triangles are made in this polygon when all of the triangle's interior angles are portions of the original polygon's interior angles. So there are 3 triangles in a pentagon, and all 3 triangles' interior angles add up to 180 degrees. So here's one way of looking at it, just by adding 180 3 times. That's 540. Now that's what we would have done. If this was a 5-sided shape, which it is, we're going to do 180 times 5 minus 2. So that is, once again, 180 times 3, or 540. Doesn't matter which way you do it, but at least now, even if you forget the formula, you can make more sense of that's why it is what it is. Number 23, we need to find out x, y, and z. X and y can be found out pretty easily here because they're linear pairs with their exterior, well, y is an interior angle, 80 is an exterior angle. So y is 180 minus 80, which is 100. X is an exterior angle to this interior angle, but it's 180 minus 95, which is 75. No, that's not, well, what is it? It's 85. So x is 85 degrees. Now z, you don't know this exterior angle here, so but now you can do this in one of 2 ways. Either I can add up all of the interior angles here, and I'd still need to know this one. I think that's 118, 180 minus 62. I could add all these in this one here, add up all of these guys right here, and these 5 should equal 540, correct? Because this is a 5-sided shape. So if I add up 100, which is y, with 118, with 95, 127, and z, I'm getting 540 degrees. Good time to go to the calculator. Let's go ahead. That's, well, let's see, 218 plus 95. I'm just going to make sure I get this correct. Plus 127 is 440. So subtract 440 from 540, you'll get z is 100. So that's one way of doing the problem. Where z is 100. A second way of doing the problem is using the exterior angles. Now I had to solve for x to make the exterior angle thing happen. But what I would have to do here is say, I'm going to create another variable called w. If I add all the exterior angles of any polygon, doesn't matter how many sides there are, but if I add all of these guys up on the outside, I should be getting 360 degrees. Doesn't matter how many angles there are in the polygon, once again. So 80 plus 62 is 142, plus 85 plus 53, that becomes 280. Whoops, equals 360. Subtract 280, you're going to get w equals 80. Now that w is 80, you would then use that 80 to find out what z is, as these are a linear pair, and 180 minus 80 is 100. So 2 different ways to find that out. They both work, they both apply, they should have both been talked about because you might have to use that at some point. Okay, let's sketch these pairs of lines, tell whether they are parallel, perpendicular, or neither. I'm going to go pretty quickly through them. After I explain one, the other should take care of themselves. Y equals 4x plus 7 has a slope of 4 over 1 and a y-intercept of 0, 7. So I'm going to start at 7. And I would probably go up 4 over 1. The problem is here, I'm kind of running out of room. So let me go down 4 and to the left 1. Down 4 to the left 1, etc. That'll be just as fine. I just need to be able to draw a line that goes through them. And let's make it purple. Let's make it very liney. Okay, so this will go through like that. And that's the first one. The second one, let's make blue. This is negative 1/4 x minus 3. So your y-intercept is 0, negative 3. Okay, so let's start at negative 3. And fraction shouldn't be too bad for slope, just going down 1/4. Pretty good idea of what to do there. There's not really a problem with fractions when it comes to slope. In fact, some people really prefer it because it tells you exactly how much it is you're going, in this case, down and over. Whereas when it's a whole number, maybe sometimes you forget that you have to run after you rise. So little things like that, right? Anyway, so you graph this, and then you determine, are these lines perpendicular? Now, you won't do it by looking at them, but if I do look at them, you know, they do look perpendicular, at least close enough. But you figure it out based on whether your slopes are opposite reciprocals of one another. M in the purple is 4/1. M in the blue is negative 1/4. Opposite means changing the sign from negative to positive and vice versa. Reciprocal means flipping the 1/4 to 4/1, flipping the numerator and denominator. So that is true. So yes, they are perpendicular. I guess I shouldn't have asked, are they perpendicular? I should have asked, are they perpendicular, parallel, or neither? Perpendicular. But I know they're not parallel because they intersect. So like I said, I'll work a little bit faster this time. Let's go ahead and sketch. So the first one will be in blue, 3x minus 4. Start at negative 4, go up 3/1. Quite a few times. Do it as much as you can fit on your graph. That's always a good recommendation. Something close to it. Draw the line through. Now you might already know what the answer is as far as whether it's parallel or perpendicular, but you still have to graph it anyway. Let me answer that for you as I'm graphing this next one at 3x plus 1. When lines are parallel, their slopes are the same. So these slopes are both 3, and also to be parallel, they have to have different y-intercepts. That's kind of an important part, because if they had the same y-intercept, they'd literally be the same line. We can't have that make the lines parallel. Those wouldn't be. Those would be the same line. They would be intersecting everywhere. But these lines have the same slope, therefore they are parallel, and those are the graphs. As you see, they will never intersect. This will always be above it, just a little bit more. That's number 25. Number 26, y equals x plus 5. That's really 1x plus 5 in case you were curious. So that slope is 1/1. So as I start at the point 0, 5, my slope's going to go up 1/1, up 1/1, etc. And down 1 to the left 1. And if I use my line tool, I can actually do this pretty quickly if I just make sure it goes through all those and through all these as it's going down. So there's the first one. The second one here, let's use a color I don't use very often. Let's use this blue. 5x minus 1. That's 5/1. So starting at 1, or negative 1 here. You know what? That no wonder I use other colors. They're a lot easier to see. And I got to go up 5/1. Up 5/1. Notice how this slope is a lot steeper than the first one. And now we know they're not the same slope, so they're definitely not parallel. And you can see this as I'm about to draw this. And you also can probably assume they're not perpendicular. You take a look at it and you're like, yeah, definitely not right angles being made right there. But they do intersect, and they have different slopes. It's neither. They are neither perpendicular nor parallel, but they do intersect at a point. Last one, 27, we have y equals negative 3 and x equals 10. It might help to rewrite this one as y equals 0x minus 3, because it's good to think about this in terms of mx plus b form. That's how I did the last three. So I start at negative 3 on the y-axis, and this slope is 0 over any value. Let's make it 1. 0 is 0/1. So this is rise over 1. I'm going to go up 0/1, up 0/1, etc. This keeps going along this track. Now this is interesting for most people because they take a look at that and they say, why is y equals a horizontal line? Well, that's just the way it works, because although you traverse up and down on y to figure out what y value you want to look at, this is y equals negative 3. And no matter what x equals, y will always be negative 3. That's the height. The direction these are going is not related to the height which it is. Well, I mean, it is, but I mean, we're not going up and down just because the y-axis is up and down. The line y equals -3 is down here because that is the height of -3 at y. Now, if you imagine that y is horizontal, then x is vertical. And there is no y value here, so there's no slope to which we're referring to. In fact, it's an undefined slope because x equals 10 is all the way here. You can't even see it, but at 10, there's a vertical line up and down because no matter what y is, x is always going to be 10. Whether it's just right there, or whether it's down lower, like at -3, or whatever else, way down there. Now, this question's not asked, but where do these points intersect? They intersect at 10, -3. If anything else, here's a way that you can remember that one's horizontal, one's parallel. This is the x value, this is the y value. X equals 10 and y equals -3, and that's where they intersect. And that makes sense. Even though y isn't vertical and x isn't horizontal, it should still connect in such a way that you can make sense of it. So let's see, y was blue, x was red. Now, are they parallel, perpendicular, or neither? Well, I talked about how this one has a slope of 0, and I talked about how this one has an undefined slope, x, and undefined only happens when you divide by 0. Like 1 divided by 0 is undefined, stuff like that. You know, up 1 over 0, up 1 over 0, up 1, etc. So now these aren't, if I make that negative, that might help. Down 1 over 0, etc. These are opposite reciprocals of each other. It's hard to mention slope when you're talking about something undefined because it doesn't really have one, but all vertical and horizontal lines are perpendicular to each other. So that's probably something good to know. So these ones are perpendicular. There we go. I think this is the last problem here now. What is the measure of an exterior angle of a regular 12-gon? 12-gon is also called a dodecagon, in case you weren't certain. But for any n-gon, okay, for any n-gon right here, we want to know how many sides there are. So that's what they're talking about. It's a 12-sided shape. And I wouldn't bother trying to draw one myself, but I think I can create one right from here. Now this is a regular 12-gon, and regular means all sides and angles are congruent, so this one actually happens to be that as well. So it means this angle is congruent to this one, etc. All of these are the same measure. Now, same with the exterior angles. If the interior angles are congruent and the exterior angles are all supplementary to the interior angles, then all the exterior angles are congruent to each other. So what we want to find out is the measure of one individual exterior angle of a regular dodecagon. Just one of them, just one of those x's. Well, if all of these are the same, then there are 12 x's, 12 exterior angles, and when you add them all up, the sum of the measure of exterior angles adds up to 360 degrees. So all you have to do is divide by 12 there, and I don't know what that is. At 30, right? So x is 30 degrees. So each exterior angle measure is 30 degrees for that one. If you want to find the measure of each interior angle, you have to find out what the sum of the measure of the interior angles in a dodecagon is first by doing 180 times 12 minus 2. And then you could then divide by how many sides there are, or angles there are, to find the measure of just one of them. So in this case, even though this isn't your answer, I'm just helping you out, 1800 divided by 12, what is that, 150? 1800 divided by 12, 150. So that would be the measure of each interior angle. Or what you could have done, which I just thought of right now, I honestly didn't think of it before, is if you know this is 30 now, then the interior angle measure is supplementary to it. Subtract it from 180, subtract 30 from 180, you get 150 there. Remember, that's for a regular one. All sides and angles congruent. If they're not congruent, you're going to have to do a little more work like we did way back here, and have to add them up individually to find different things like that. Otherwise, if it's regular, you get to divide by the number because they're all going to be the same. And that's it. Fine.